Hello, everyone. Again, this is Professor Barish, and welcome to part 2 of our course, the online version of it. I hope all of you are safe and well. And this video today is going to be recorded for the 2 colleges that I teach at, both Rowan University and for Camden County College. Both groups of students are learning the same topic at the same time. So at least for today, I'll be doing this video for both groups. For the Camden County College students, what I'll be reviewing today is in section 5.4 of your textbook. It's called Sampling Distributions. And for the Rowan University students, it'll be chapter 8, which will be on sampling distributions. Also, in your MyLab, and this is just for Rowan University students, not for Camden County, the MyLab part of the course, it's lesson number 13. I'll be sending the Rowan University students an email today describing what sections that you'll be doing in MyLab. For Camden County students, I will be assigning section 5.4 in MyLab. Okay, so hopefully that's clear to everybody. So today's going to be on sampling distributions, and I'm going to go back and forth between the 2 textbooks today. So I'll mention which textbook I'm looking at. Both textbooks offer some good definitions, good examples, and so forth. So, and I also have some PowerPoint slides that I'll show you. This comes from the Rowan textbook, but I think it equally is useful for the Camden County students. All right, so we'll see how far we can get today, and if I feel like a second video is required later this week, I will make a second video for you guys. It's possible the second video could be one for Camden County and one for Rowan. We'll see how it goes. All right, this is sort of new ground for me. All right, so here we go. All right, we'll get started. And hopefully you have your textbook nearby. You have your TI 83 or 84 calculator nearby, maybe some paper and pencil that you can take notes. Obviously, you'll be able to use these videos and rewind and so forth, so you can review things that you've seen earlier. You may find that actually very useful for your review. So anyway, what we're going to cover today is something brand new. It's called sampling distribution. If you remember, the last section of the course is on probability, and we talked about probability distributions. And the probability distributions that we talked about, such as the normal distribution and the binomial distribution, were basically for cases where we were looking at probabilities for selecting one person or one individual from the population. And that was the purpose of doing that. From this point forward, what we're going to be doing is we're going to be looking at samples of people or samples of things instead of just one person or one thing. Okay, so we have to find a way to answer probability questions for a sample as opposed for an individual. So that's what today's all about, describing what this thing called a sampling distribution is, and then applying it a little bit today. And then we'll do some more problem solving on the next video. All right, so we'll know how to apply it. And then starting on next week, we're going to be talking about what's called inference, specifically it's called confidence intervals. And we'll be using this idea of a sampling distribution starting next week. So it should be an interesting way of learning. I think typically this is a topic we certainly want to learn in person, but given the circumstances, we'll have to do it this way. So let's see how it works. All right, so let's go to one of the textbooks. I guess maybe we'll go to the Rowan textbook, and I'm going to turn on my share screen now. And hopefully you'll be able to see this textbook. This is the Rowan University textbook. But again, for all of you students who are from Camden County College, this certainly will help you also. The first thing that we want to define, this is something we talked about earlier in the course, is what's called a statistic. A statistic in this textbook is a quantity computed from values in a sample. So we take a random sample, and maybe we're measuring the heights of 50 people in the sample. Okay, so an example of a sample statistic would be finding the mean or average of those 50 heights. So that would be called the sample mean, right? Now, I had mentioned this earlier in the course, but you could picture that maybe one student in a class could measure the heights of 50 people, maybe from a population. And then somebody else randomly samples 50 people from a population and gets completely different 50 people. And so the quantity called a statistic, in this case a sample mean, or sample height, or the mean height of those 50 people, would be different for maybe student number 1 or student number 2, because they're sampling for 50 different people. So you can picture that the sample statistic, the sample mean, would be different from sample to sample. Now, if we could list all possible samples of size 50, that is, all possible collections of 50 people from a population, and measure their heights for each of those 50 people in each sample, and then find a sample mean or average height for each of those samples, you can picture that we could make a list. For every single possible sample that's out there, we can make a list of all of these sample means. Now, the fact that the means change from sample to sample is what's called sampling variability. According to this book here, the observed value of a statistic, that is, we select 50 people, we find their heights, we average their heights, that's the average height. So the observed value of the statistic depends on the particular sample selected from the population, and it will vary from sample to sample. So this is called sampling variability, and we'll illustrate this in a second with our PowerPoint slides. Okay. Now let's actually go to the other. Let's see where it is. Here it is. This is the Camden County book. Oops, that's not it. Just give me a second. I think it's behind this little screen here. Here we go. And just keep me signed in. I'll say yes. All right. So again, this is the Camden County book definition of a sampling distribution. Here it says a sampling distribution is the probability distribution. Notice they use the word probability here, of a sample statistic that's formed when random samples of size n, that's a number of people or individuals in the sample, are repeatedly taken from a population. If the sample statistic is the sample mean, then the distribution or list is of all of these sample means is called the sampling distribution of sample means. Each sample statistic has a sampling distribution. All right. So that's the definitions there. Let's see if there's anything worthwhile here. Let's hold off on looking at the mean and standard deviation for a moment. And let's go to the PowerPoint slide. So let's look at an illustration of all of this. Let's actually get to the slideshow. Okay. So in the slideshow here, they're going to define what a statistic is. A number that can be computed from sample data, sample mean, we just talked about that a minute ago. You can actually find the sample standard deviation, right? We've done this before. We're not going to be actually finding a sampling distribution for a standard deviation, but it can be done. What we will be doing a little bit later, next time probably, is look at what's called a sample proportion. Okay, and we'll define what that is next time. But what we're going to be doing mostly is working with sample means today. Now, for the Rowan University students, the homework is dealing with sample proportions, but I think I already defined to you guys what a sample proportion is. For the Camden County students, I have not done that yet, so that'll be done later video. Okay. So the observed value of the statistic depends on the particular sample selected from the population, and it will vary from sample to sample. And as I said a minute ago, that's called sampling variability. All right, so now we've looked at all of these definitions from different sources. Hopefully you know what I'm talking about now. So let's look at this very simple example. I like this example because I think it's so simple, and we're not dealing with any complicated type scientific thing or anything. That's a very simple example. So picture a college, they call it Wolf City College, and it has a fish pond. And suppose there are 20 fish in the pond. So the 20 fish is our population. That's the population of fish in the pond. There's 20 of them. The lengths of the fish in inches are given below. So what's listed below are the lengths of each of the 20 fishes. All right. So there they are. So for the first number here, this number here, this particular fish is 4.5 inches. The next one's 5.4 inches, and so forth. All 20 of them are listed here. I think all of the numbers are pretty different from each other, so that makes it a little easier. So that's a population of fishes. There are 20 of them. So suppose we randomly catch a sample of 3 fish from this pond and measure their lengths. What would be the mean length of that particular sample? All right, so you have to get the idea. There's 20 fish in the pond, and let's say we randomly catch 3 of them. All right, so some random process we catch the 3 fish. All right, so that's our sample size. It's n is equal to 3. All right. So suppose we catch these 3 fish. All right. Well, the first fish here has a length of 6.3 inches. I think it's this fish right here. The second fish has a length of 2.2 inches. That's this fish right here. And the third one has a length of 13.3 inches, and that has a length that's this fish right here. All right, so those are the 3 fishes. So now we're going to find the average length of these 3 fishes, and or 3 fish. I guess I should say fish, not fishes. As a child would say fishes, and I think fish means more than one fish. Anyway, to find the average, as you know, you just add the 3 numbers up and divide by 3. And when we do that, we come with the sample average of 7.27 inches. All right. Let's suppose and that's called a statistic, by the way. The population average is called a parameter. And okay, so everybody knows that parameter. And the sample statistic is called, this is the sample mean is called a statistic. All right. All right, let's do another sample. So suppose somebody else comes along and catches 3 different fish. These are different fish than the first from the first sample. So the first fish is 8.5 inches. And where are you? That's this guy right here. The second fish is 4.6 inches. And this is that guy. And 5.6 inches is the last fish. So 3 different fish are caught in this particular sample. And the average of these 3 numbers is 6.23 inches. Suppose somebody else comes along and catches these 3 fish with these lengths, comes up with an average of 10.7 inches. So this is sampling variability, isn't it? Here's 3 different samples of 3 fish from a pond of 20 fish. Okay? And each of those samples has a different average length. Okay? Sampling variability, that's called. Now, if we averaged all 20 fish here, in other words, added up all 20 of these numbers and divided by 20, we would get the population mean. It says true mean here, but that's the population mean of 8 inches. And notice that none of these three samples is equal to 8 inches. The one that's closest to the 8 inches is this first sample of 7.27 inches. And then the second sample and the third sample are further away from the actual mean. Okay. So you can see sometimes the sample mean is bigger than the population mean. Sometimes it's smaller than the population mean. All right. Move on. We now see sampling variability. Now, how many different samples can we have in this case? In other words, from the 20 fish, how many samples of size 3 can we get? Well, some of you, maybe not all of you, some of you might have studied this idea of combinations, maybe when you took high school mathematics. But if you didn't, that's fine. It's not required for this course. Your TI-83 and 84 calculator calculates this for you. But anyway, when you do this calculation, what this is saying is, out of 20 fish, how many combinations of 3 fish are there? And there are 1,140 different possible samples of size 3 from this population. That's quite a bit. So picture listing all 1,140 samples of size 3, finding their means. In other words, there would be a mean or average for each one of those samples. There would be 1,140 means, wouldn't there? All right, so with the list of all 1,140 means of sample size 3 is what's called a distribution of all possible means, okay? And we call that a sampling distribution. So a sampling distribution is a list of all possible sample statistics of a certain size. In this case, the sample mean of size 3. All right. All right. So this is called a sampling distribution of X bar. Now there's a little bit of a mistake here. So I'm going to, this line that should be above the X here ended up being crossing the F there. So it should look like this. The sampling distribution of X bar. Okay. So the distribution that would be formed by considering the value of a sample statistic for every possible different sample of a given size from the population is how we define the sampling distribution. We talked about that earlier. Now, the sample statistic in this case is a sample mean. We'll learn also how to do this for a sample proportion in a later video. Now, to make this easy, what we're going to do now is find another pond that only has 5 fish in the pond. So there's 5 fish now instead of 20 fish. That's our population. We're doing this as an illustration so that we can actually do some calculations with this. Now the lengths of the fish are given below. 6.6 inches, 11.7 inches, 8.9 inches, 2.2 inches, and 9.8 inches. So that's our population, all right? Population. Now, what's the mean and standard deviation of the population? Well, you know how to do this, right? You can take those 5 numbers, put it into a list into your TI-83 or 84 calculator, go to one variable statistics, and look up the mean, right? So the mean in this case, this is a population, we would use the symbol mu. Now, they use a little x here to show that it's for a population. Some of your textbooks don't have the x in it. And it's 7.84 inches. That's the mean, the population mean. And that's called a parameter. All right? So that's the population mean. That's the population standard deviation. It's sigma x. Again, we would read that right out off of our TI-83 and TI-84 calculator. Okay. And you could try that now, just entering those 5 numbers into your calculator. Take a minute to do that as I sit here and and think about what the next step is for me to talk about. You can enter those into your calculator. These 5 numbers. Once you've done that, go to one variable statistics. And if you have an 83 calculator, just put the list in that your numbers are in, hit enter. If you have the 84 calculator, you'll just put in L1 for the list. Make sure the frequency list is not blank. Okay. So you would get the 7.84 inches. All right. Okay. And the mean standard deviation is 3.262. All right. So you all should have those numbers in one variable statistics. So what are we going to do now is we're going to take samples of size 2 from this population of 5. How many samples of size 2 are there? There they are. Okay, there's how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. There's 10 of them. Okay, this particular one is we're pairing 6.6-inch fish with a 11.7-inch fish. And then maybe the last one would be the 2.2-inch fish and the 9.8-inch fish. Okay, so these are all different possible combinations of 2 fish that we can get from a population of 5 fish. All right. If we added these 2 numbers and divided by 2 for each one of these samples, these would be the means. So we have 10 samples, possible samples of size 2, and we have 10 means for each of those samples. We have a mean for each of these samples. There's 10 of them. All right. Now here's the big deal. Okay. So this is number one. This is the sampling distribution of sample means. All right. These 10 sample means. All right. What is the mean and standard deviation of these sample means? In other words, if you put these 10 numbers, these 10 sample means into our calculator, again, you can do this a little bit later, right, to confirm what's on the slides here. You put these 10 numbers into your calculator and divide by 10. So if you put the 10 numbers into the calculator and go to one variable statistics, we can look up the mean and the standard deviation. Now make sure when you look up the mean, that the standard deviation, you use sigma, not S, because this is a probability distribution that we're looking at here. Okay. So when we do that, the mean, now look how they write the mean here. They use mu, which is a population symbol for a mean, but they use X bar here. Mu X bar. That is, we're finding the mean of all the different samples, all the different sample means. We're taking the mean of the sample means, averaging all 10 of these sample means. We get 7.84 inches. That's called the mean of the sampling distribution of means. Okay, mean of the sampling distribution of means. This is the standard deviation of these 10 numbers. Notice we use sigma here because it's a population of sample means. Okay, so we're using sigma X bar, 1.998. Now notice something really interesting. Notice that the mean of all the sample means and the mean of the population is that same number, 7.84. And this is true for any sampling distribution from a population. Okay, it doesn't matter what the sampling distribution is. If you can list all the different samples of size n, and all right, and list their sample statistics, each one of them, and average all of them, the average will be equal to the average of the population. So the average of these 5 numbers is mu x, 7.84, and the average of these 10 sample means is 7.84. So the mean of the population is equal to the mean of the sampling distribution. That is always true. Also notice that the mean of the sampling distribution is less than the mean of the population. And that will always be true if the sample is at least of size 2. All right, we will always see the mean of the sampling, the standard deviation of the sampling distribution to be lower than the standard deviation of the population. Okay. All right. Now let's do samples of size 3 from this population of size 5. So how many samples of size 3 are there? Well, here they are. And it's a coincidence, but there's also 10 samples of size 3, all right? Doesn't mean there's always 10 samples of size whatever, all right? It could be smaller number of samples, it could be a larger number of samples, but this is just the way it works out. So here are the triplets, all right? The triplets of 3 fish that are taken from the pond. For example, this first one here is 6.6 inches, 11.7 inches, 8.9 inches. The last one is 8.9 inches, 2.2 inches, and 9 inches. So these are the list of all 10 possible samples of size 3 fish that are sampled from the pond that has 5 fish. And these are the means for each of these 10 samples. And the mean is just simply adding the 3 numbers up and dividing by 3. All right, once again, we're going to find the average of the sampling distribution. In this case, this is a different sampling distribution because it has samples of size 3 in this case here. But notice that the mean of this is exactly equal to the mean of the population once again. And this is always true. The mean of the population is going to be equal to the mean of the sampling distribution. And what is the standard deviation? Notice in this case, it's even lower than before. Did you notice it was like 1.89 or something like that before when we had samples of size 2. Now with samples of size 3, notice that the standard deviation of the sampling distribution is even lower. That's something that's always going to be true also. All right, so we're going to look at that in a couple of minutes. All right. So what do we notice? That the mean of the sampling distribution equals the mean of the population. Always true. As the sample size increases, the standard deviation of the sampling distribution decreases. Always true. So as n increases, sigma x bar decreases. General properties of sampling distributions of sample means. That's rule number 1. Here is rule number 2. Okay, now we're going to talk more about this next time. All right, we'll do some examples next time on this. But rule number 1 is that the mean of, again, the mean of the sampling distribution is equal to the mean of the population. And notice that this formula here. This is something new. Right? It says this formula is exact if the population is infinite. Well, I don't know about you, but I don't know many populations that are infinite size. There's usually a finite limit to the population. All right. So this formula is approximately correct. If the population is finite, that means there's a limited number of people or things in the population. And this is important here. And no more than 10% of the population is included in the sample. So if the population has 1 million people, all right, 10% of 1 million is 100,000. Well, most likely our samples are going to be a lot lower than 100,000. So in most cases, when we do sampling, there's types of examples I'll be showing you in the future. Percentage of the population that's in the sample is going to be much lower than 10%. Now, the example that I just showed you where we had a population of 5 fish, and we were taking samples of size 2, well, 2 divided by 5 is 0.4 or 40%. Well, that is way too high, so this formula wouldn't work in that case. But again, most of the situations we'll be looking at, this formula we can use because the sample size will be much less than 10% of the population size. All right, so these are the 2 rules we're going to be using whenever we're looking at the sampling distribution of X bar. The mean of all of the sample means is equal to the mean of the population, and that the standard deviation of all of the sample means is equal to the standard deviation of the population divided by the square root of the sample size. That's okay. All right. Now they do give an example here, which we can go through. So I think we have time to go through this one example here. And then I will look through the textbook to see if there's anything else that we need to do today. Otherwise, I will do a second video where we're going to be doing more problem solving using our TI-83 and 84 calculators. All right, so make sure, again, for next time, that we definitely have those calculators ready to go. But I'll show you a little bit today of how to apply this. So this is an example of a more complicated case here. It's a scientific paper, talks about the mean platelet volume in patients with metabolic syndrome and its relationship with coronary artery disease. That is a big mouthful of words there. And what it says here, it includes data that suggests that the distribution of platelet volume of patients who do not have metabolic syndrome is approximately normal with a mean of 8.25 and a standard deviation of sigma equal to 2.75. All right, now these are population parameters here. The mean mu means population. The sigma here, population. This is population mean, population standard deviation. Regardless of all these words here, if you find your head spinning when you read all these words, don't worry about it. Whenever you're looking at a problem, what you're going to be doing is you're going to be looking at the words mean, the word standard deviation, things like that. Anyway, what we're measuring here, they say, is approximately normal. Okay. So here's the mean of 8.25, and there's our standard deviation 0.75. Notice that the value 9 is one standard deviation higher than the mean. The value 7.5 is one standard deviation lower than the mean, right? So we've all seen this normal curve before, all right? And they use this software program called Minitab to generate this curve here, all right? All right, now this is just to illustrate the idea that the bigger the sample size, the narrower the distribution looks for the sampling distribution, okay? So here is a sample size of five people, 5 patients. All right, looks kind of normal, doesn't it? This is for 10 patients. Also looks normal, but do you notice that the spread of the data is much smaller? Even if you just calculate the range here, the range is smaller than over here. The range here is 9.2 minus 7.2, which is 2. And the range here is definitely less than 2. N is equal to 20. Again, looks approximately normal, but notice that the range is even narrower, right? And then for N is equal to 30, it actually looks beautifully normal, and it has even a narrower range, right? So notice here that as the size of the samples goes up, the sampling distribution's standard deviation goes down, right? Let me repeat that. As the sample size goes up, the standard deviation of the sampling distribution, this X bar here, the distribution here, the standard deviation goes down, all right, goes down. Notice, however, that the mean is approximately the same, should be the same, exactly the same for each one of these cases. Okay, the means are the same, standard deviations get smaller. Shapes are all approximately normal. Here's rule number 3. When the population distribution is normal, the sampling distribution of the sample means is also normal for any sample size. That's rule number 3. All right. Okay. Here's another example. There's data on has to do with NHL games. This is hockey, National Hockey League. All right. And they're looking at what? On the time in minutes from the start of the game to the first goal scored. Okay. Notice here that in this case here, this looks horribly skewed. It's a skewed right, isn't it? They call it positively skewed. It means the same thing. It means the tail is going towards the right. Has a mean of 13 minutes and has a median of 10 minutes. Okay, but it's skewed. It's skewed. Now, let's take a look at sampling distributions, different sample sizes. Where again, we're going to be using sample size 5, sample size 10, sample size 20, and sample size 30. Now, once again, these are histograms, aren't they? Histograms that we're looking at. All right. Now, even at sample size 5, this does not look as horribly skewed as the population does it? This is the sampling distribution of sample means of size 5. Still tails a little bit to the right, but it's much less skewed than the population. Here's samples of size 10, looking closer to normal, slight skew to the right. 20, still skewed a little bit to the right, but not so badly. And now let's look at size 30. Beautifully normal, right? Now, nothing's perfectly normal, but it's beautifully normal. Hardly any skew at all there. So once again, if you go back, there's our population histogram, very skewed to the right. And look at these, look at when n is equal to 30. The sampling distribution is approximately normal. All right. All the means, again, approximately the same. Standard deviations, now notice that standard deviations get smaller also, right? As the population, as the sample size gets larger. So the means are about the same. Standard deviations get smaller as n gets larger, and the shape more and more normal as n increases. And this property is called the central limit theorem. When the sample size is sufficiently large, the sampling distribution of sample means, x bar, is well approximated by a normal curve, even when the population distribution is not itself normal. It could be horribly skewed. And that means that we can use normal CDF with our calculator for the sampling distribution, even though we can't use it for the population because it's so skewed. How large is sufficiently large according to this? Central limits theorem says you can safely apply it, this idea, if the sample size is at least 30. Now here it says exceeds 30, but if it was 30, I'd say go ahead and use it. So greater than or equal to 30, you can apply this central limit theorem and say that even if you know nothing about the population, the shape of the population curve could be horribly skewed. We could say that if the sample size is at least 30, the sampling distribution is approximately normal. That's called the central limit theorem. Okay. So here's another example here. A soft drink bottler claims that on average, cans contain 12 ounces of soda. As you probably know, this is a manufacturing process, right? When you make soda, so even though it says there's 12 ounces of soda in there, there could be slightly less, slightly more than 12 ounces in there. So let X be the actual volume of soda in a randomly selected can. Suppose that X is normally distributed with a standard deviation of 0.16 ounces. 16 cans are randomly selected, and the soda volume is determined for each one. Let X bar be the resulting sample mean amount of soda, all right? Okay. If the bottler's claim is correct, then the sampling distribution of X bar is normally distributed with a mean of 12. Now, where do we get the 12 from? Well, it says the bottler claims that on average, the can contains 12 ounces of soda. Some of them have a little bit less, some have a little bit more, but on average is 12 ounces of soda. That's the population mean. We're assuming the population standard deviation is 0.16 ounces. That's the average spread of the amount of soda in all the cans. Okay. Now, 16 cans are randomly selected. Can we use, in this case here, the central limit theorem? Well, the central limit theorem says it needs at least 30 cans. But, and this is the big exception, if we can assume that the population is normally distributed, which it says down here, or actually, where does it say it? Oh, up here in the body of the problem. So suppose that X, which is the amount of soda in any can, is normally distributed. If the population is normally distributed, we're going to assume the sampling distribution of sample means is also normally distributed. And so if we pick 16 cans, which is less than 30, we don't have to worry about the central limit theorem in this case. All right? If the population is normally distributed, it doesn't matter the size of the sample. The sampling distribution will be normally distributed. That's the rule. Okay? So what is the mean of the sampling distribution? It's equal to the mean of the population. It's equal to 12. What is the standard deviation of the sampling distribution? It is the population standard deviation divided by the square root of the sample size, which in this case are 16 cans in the sample. So 0.16 divided by the square root of 16 is 0.04. Notice how much smaller the standard deviation of the sampling distribution is than the standard deviation of the population. Okay? Now, here's the big question, and this is something that we will look at for a couple minutes. They say, what is the probability that the sample mean soda volume is between 11.96 ounces and 12.08 ounces? Now, what are they asking you? They're saying, what's the probability that the sample mean? So in other words, if we take a random sample of 16 cans, let's say we're not doing that yet, all right? In other words, we're going to take a random sample of 16 cans. We want to know what's the probability that the mean of the amount of soda in those 16 cans is going to be between 11.96 ounces and 12.08 ounces, all right? So you get the idea, we haven't calculated the sample mean yet. You want to know ahead of time, if we did pick 16 cans out, randomly selected 16 cans, what's the probability that the mean soda content of those 16 cans is between 11.96 ounces and 12.08 ounces? And that is what we're being asked. Now notice that in the middle here of this probability statement is X bar. Now up to today's class, we were asking probability statements that have X in the middle. X, not X bar. So before we would say we selected one person or one can from the population, what's the probability that its soda content is between 11.96 and 12.08 ounces? We would have used X here because it's for one can. But here, we're putting X bar here. We're saying, what's the probability that the mean of the sample, the mean of those 16 cans, is between these two values? It's a different question. And what we must use, and this is what we're going to do next time, what we must use is the sampling distribution of sample means. That's what we're going to use to answer this question. And since the population is normally distributed, we're going to use normal CDF with a calculator to answer this question. All right? So that's what we're going to do next time, and we'll do lots of examples next time using your calculator. So let's actually go to our other textbook. I'm going to go out of this slideshow right now. Here we go. And let's go to the back to this textbook here. And let's see if there's anything in here that would be useful for you. Well, there's our formulas that we were talking about before. And now this is for the this is our Camden County textbook, by the way, not our the Rowan textbook. The mean of the sample means is equal to the mean of the population. The standard deviation of the sample means is equal to the standard deviation of the population divided by the square root of the sample size. One thing that they talk about in the book here, which I do want to make mention to you, because we will mention this at a later date, that this formula here, this standard deviation of the sampling distribution of sample means, this is called the standard error of the mean. For the Camden County students, you might see this on a quiz, an upcoming quiz, called the standard error of the mean. Okay, so that's just a definition. All of you, even the Rowan students should know that. Let's see if there's anything else here that would be worthwhile looking at. I'm just going to flip through really quickly. Here is another way of defining the central limit theorem. Okay. All right. So once again, it mentions number one here. If we have random samples of size n, where n is just move this over if I can. It's just like this. Up a little bit. There we go. If random samples of size n, where n is at least 30, are drawn from any population, and the sampling distribution of sample means approximates a normal distribution. However, it says number two here, if we draw the sample from a population that we know is normally distributed, then n doesn't have to be greater than or equal to 30. It could be any sample size. You can have size of 15, you can have size of 5, it doesn't matter the sample size. All right, so that's, we had reviewed that earlier, but this is another, for you guys in the county, this is in your textbook. And again, here's our two formulas here. And once again, they give you examples, humorous examples. Here's a population that looks like somebody lying on their back, snoring. This is their nose, and this is their mouth. This obviously is not normally distributed, but the sampling distribution would be normally distributed as long as n is at least, I'm sorry, this is it. So if this is our population, and then as long as n is greater than or equal to 30, our sampling distribution is going to be approximately normal. If the population is normal, then it doesn't matter what the sample size and the sampling distribution. The sample means will also be normal. Okay. All right. And then there's some more things in here for you Camden County students. Once again, look through the examples in the textbook. Again, we're going to be doing plenty of examples next time. Using some of these examples in this book, this is very good, what we're looking at here. Well, let's just switch over to the book that's being used for Rowan. This one here. Let's see if there's anything here that would be useful for us to know as a group. And let's see anything so far. So just give me a second to flip through here to see if there's anything worthwhile looking at. Here's the definition of the sampling distribution, which we defined earlier, and that's it for 8.1. So we covered 8.1 today in the textbook for Bowen University. And what we're going to do next time is we're going to cover 8.2 and 8.2 and 8.3 for Rowan. Again, I might do a different video for Rowan next time. For Camden County, I think we'll just do some more examples in the in your textbook. All right, so I might switch over now that I'm thinking about it. Might do 2 separate videos, one for Rowan and one for Camden County, and we'll do again for both groups. We'll do plenty of problem solving to show how we apply the sampling distribution to actual problems. Okay, so I would highly suggest that you do your homework. Read the textbook. Again, for the Rowan University students, I covered 8.1 today, but if you want to also read 8.2 and 8.3 just to jump ahead, I would recommend that. Also start your homework, which I will post today. And also for the Camden County students, please read section 5.4, start doing the homework for 5.4, as I will post that also today. All right, so let's we'll stop the share here. I think things worked out very nicely today, and I guess that's it for today. And I will post this video. I'm going to try to see if I can get this posted on YouTube, and then attach it to various places in Canvas. I'll have to see where to put it in Canvas for Camden County students, and in Blackboard for our Rowan students. So again, I'll send you guys separate emails today letting you know where it will be posted. All right, and that is it for now. So hope this went okay. Again, you'll be able to review this video once again. If you are not sure what you learned today, certainly you can look at other videos that are out there, but I would strongly suggest that hold off on that now, because most of the other videos that are out there are doing more problem solving, and that's what video number 2 will be doing. So for those of you who feel like you need more problem solving, don't worry, I'll be recording another video this week, which will help you with that. And again, we'll be having Q&A sessions separate for Camden County and for Rowan University later in the week. I will let both places know, both groups of students know through email when that will happen. It will probably happen Thursday or Friday, but I'll have to make that determination based on my schedule. All right, and then we probably won't be using Zoom for that. Although we could, I mean, it's possible we could use Zoom for it, but I think there is a 40-minute limit with Zoom if there is more than 2 people on the video conference. So, but again, I'm going to play around with the different video elements for both schools and see what would be the best way of doing a Q&A, and then also recording it and making it secure for just your particular college, your particular class, actually. All right, so again, look out for an email today for both the homework and for the video, and I'll be talking to you soon. All right, and that'll be it for today. Thank you.